Welcome back to the course on software-defined networking. In this lesson, we're continuing our discussion of the control and data plane separation, and in particular, we're talking about the challenges associated with separating the data and control planes. We'll overview several challenges associated with the separation of the control and data plane, including scalability, reliability, and consistency. And we'll talk about approaches to solving these problems in the form of two different systems, the routing control platform and ONIX. Let's first take a look at some of the scalability challenges faced by the routing control platform and the approaches that that platform takes to solving some of these scalability challenges. So one of the problems that the RCP faces is that it must store routes and compute routing decisions for every router across the autonomous system. And a single autonomous system may have hundreds to thousands of routers. So that's potentially many routing tables and a lot of routing computations all being performed at a single node, whereas before all those computations were distributed across the routers themselves. So some scalability principles from the RCP design. The first is to eliminate redundancy. So rather than storing a routing table for every single router in the autonomous system, the RCP stores a single copy of each route. And if those routes are duplicated across the routers in the autonomous system, as is commonly the case, that redundancy can be represented by storing pointers into a common data structure. The second principle is to accelerate lookups by maintaining indexes to identify the particular routers that may be affected by a change in network conditions, such as the advertisement of a new route or a node or link failure. Therefore, when a particular event happens, the RCP only needs to compute new routing information or routing tables for the routers that are affected by that change, rather than recomputing the state for the entire network. Finally, RCP tackles some scalability problems by simply punting on performing routing for all the routing protocols in the network and simply decides to focus on performing interdomain routing alone. The ONIX network controller applies a couple of related principles to handle scalability problems. The first is partitioning, whereby an ONIX controller might actually only keep track of a subset of the overall network information base or network state in the network, and then apply various consistency protocols to maintain consistency across different partitions. The ONIX controller takes advantage of two different consistency models. One is a strong consistency model that ensures that different replicas are strongly consistent at the expense of some performance. The other is a weaker consistency model that is more efficient about passing information around more quickly. The second scalability principle is aggregation. So the ONIX design essentially describes the notion of a hierarchical set of controllers, such as, for example, having an ONIX controller for a department or a building across a larger enterprise network, and having a single super ONIX controller that effectively controls those subcontrollers for the overall domain. Let's now take a look at how these systems tackle a second challenge, that of reliability. So one particular approach to reliability is to simply replicate. So the RCP design advocates having a hot spare, whereby multiple identical RCP servers essentially run in parallel, and the backup or standby RCP could take over in the event that the primary fails. So the idea here is that the network would run independent replicas of the RCP, whereby each replica has its own feed of the routes from all the routers in the autonomous system. Now, if each replica receives the exact same inputs and runs the exact same routing algorithm, then it should be the case that the output or the resulting state that each of these RCPs would push back into the routers should be exactly the same, because the inputs and the algorithm are exactly the same. So in the case of the hot spare approach, there's actually no need for a consistency protocol if both replicas always see the same information. There are potential consistency problems, however, if different replicas see different information. Let's see how that might be the case. So here are two RCPs. Let's suppose that they see different information and as a result compute different outcomes or desired routing table state for routers A and B in this autonomous system. So the RCP on the left might compute an egress route for router A that says use egress router D to reach a particular destination, and hence use router B as the next hop to reach the egress router D. Now similarly, the second RCP, the RCP on the right, might install conflicting state into router B that says use egress router C to reach that destination and use A as the next hop to reach the egress router C. Now you can see that if these two replicas install this respective state into routers A and B, then we have a forwarding loop between router A and router B, because in trying to reach that destination, router A is going to use the gold route to try to egress via router D, and router B is going to use the gray route to try to egress via router C. And when each of these routers receives the packets for that destination from its respective neighbor, it's just going to bounce the packets back and forth. So what we want is for route assignments to be consistent even in the presence of failures and partitions. Now we previously just said that if every RCP receives the same inputs and runs the same algorithm, then the output should be consistent. So we want some way to guarantee that. Now fortunately, a flooding-based internal gateway protocol, such as OSPF or ISIS, as we've learned in our networking course, essentially means that each one of these replicas already knows which partitions it's connected to. Because if the RCP is participating in the intra-domain routing protocol, or the IGP, then it sees the full link state of that partition. And that information that it receives is enough to make sure that the RCP only computes routing table information or routing state for the routers in the partition for which it's connected. And that alone is enough to guarantee correctness. Let's see why. Let's suppose that we have a network partition where the routers in partition 1 can't see or can't forward traffic to the routers in partition 2, and vice versa. Now in this case, the solution would be to have that single RCP only use state from the routers in each one of these partitions in assigning routes. For example, to assign routes to routers in partition 1, the RCP would only use the set of candidate routes that it learned from the routers in partition 1. It would not use any candidate routes from routers it learned from partition 2. And that alone is actually sufficient to guarantee consistent forwarding. You can intuitively see why, because for example, if the RCP never assigned a route learned from partition 2 to a router in partition 1, then effectively partition 1 and partition 2 are simply just acting as independent networks with a common routing control platform. Let's suppose now that we've got multiple RCPs, that we've actually replicated the RCP, but the network itself has multiple partitions. Now here you might think that we've got a more serious problem, because you might have cases where there are partitions that are reachable by both RCPs or can be seen by both RCPs, but you have others that are reachable only by subsets that may be non-overlapping. Well, the approach here is to just ensure that the RCPs receive the same state from each partition that they can reach. So the IGP provides complete visibility and connectivity for each of these partitions. And if the RCP only acts on a partition, if it has the complete state for that partition, then it's guaranteed that the routes it assigns for that partition will be consistent. In other words, there'll be no forwarding loops. Let's look now at how ONIX tackles the challenges of reliability. So ONIX talks about different types of failures that may occur in the network. The first is network failures. In this case, ONIX simply just assumes that it is the application's responsibility to detect and recover from those failures. Now, if a network failure affects reachability to ONIX, the design suggests that the use of a reliable protocol or multipath routing or so forth could help ensure that the ONIX controller remains reachable even in the case of a network failure. Now, if ONIX itself fails, the solution is to take a similar approach, which is to apply replication and then use a distributed coordination protocol amongst those replicas. Now, because ONIX has been designed for a far more general set of applications than the routing control platform, a more complicated distributed coordination protocol is necessary. Some of the details of those coordination protocols are discussed in the paper that was referenced on the original slide where we introduced ONIX in this lecture. So, in summary, separating the control and data plane poses three significant challenges. One is scalability. In particular, a single controller must now make routing decisions or various control plane decisions on behalf of many, many network elements that were previously each performing those computations independently for themselves. The second challenge is reliability, that is, guaranteeing correct operation under failure of the network or failure of the controller itself. The third challenge is consistency, or ensuring consistency across multiple controller replicas, particularly in cases of network partitions or failures. So we explored each of these challenges in some detail and talked about various techniques, including hierarchy, aggregation, and various clever state management and distribution that various systems such as the RCP and ONIX have used to tackle these challenges. Each particular controller tackles these challenges in a different way, but many of these principles apply across different controller designs and implementations.